Okay, let's unpack this. Imagine you've got this massive food processing plant, right? And it's running at absolute maximum capacity. The lines are humming. There's thousands of liters of product halfway through processing. You've got a workforce of hundreds on the floor. And then suddenly the municipal pressure just drops.
Oh, yeah.
Like the incoming pipes simply run dry.
Right.
But the plant manager, he isn't panicked because they have this, this backup tank out back, so they switch over.
Right.
But the water that comes out of that tank is stagnant. It smells foul. It teeming with biofilm. And in an instant, that million-rand backup plan doesn't save the operation.
No, it destroys it.
Yeah, it shuts down the entire production line and creates a massive health hazard.
And that is the exact nightmare scenario, isn't it? I mean, for a lot of commercial operations during Cape Town's Day Zero crisis, variations of that exact nightmare became incredibly real.
Oh, absolutely.
Because a backup system that hasn't been engineered for the chemical and biological realities of standing water, well, it's actually worse than having no backup at all.
Which is exactly why we're tearing into this topic today. Welcome to this deep dive. And our mission today is highly specific, so I want to be clear right up front.
Yeah, let's set the stage.
Right. This conversation is custom tailored for South African engineers and technicians. If you are the person who, specifies, buys, or installs water treatment equipment, this is for you. We are pulling our entire focus today from one highly practical article. It's titled Backup Water.
Tanks, boreholes, and rain, and the treatment each one needs. And you can actually find that right now in the knowledge base on the DWT website.
And we really need to ground this in the stakes of our current South African operating environment. I mean, this isn't about some trendy, going off-grid lifestyle choice for fun.
Right.
When a commercial client asks you, the engineer, for a backup water system, they're literally asking you to protect their operational survival in a severely water-scarce region.
Survival is the exact word. I mean, the catalyst for modern backup planning here really goes back to that 2017 to 2018 Cape Town drought.
Oh, absolutely. Looking at the numbers from the source material, they are still shocking to read. Level 6B restrictions meant commercial water users had to cut their consumption by 45%.
And just think about the physical reality of a 45% cut. Like if you run a hospital or a manufacturing plant, you can't just operate 45% less.
Yeah.
It alters your fundamental ability to keep the doors open.
And the margin of error was terrifying. The article notes that day zero, like the point where the taps would literally be turned off and people would be queuing at collection points, that was narrowly averted by mere weeks.
Weeks, yeah.
The supply dams hit a critical 13.5%. They were staring right over the cliff edge.
They really were. But what Cape Town did was it permanently rewrote the risk matrix for the entire country. Because today, drought isn't even the primary threat anymore.
Right, it's the daily stuff.
Exactly. The daily threat is water shedding. It's these multi-day outages caused by crumbling infrastructure or pump stations tripping during load shedding and massive network pressure drops. The municipal supply is simply not guaranteed anywhere.
So if the grid is failing, let's talk about the first line of defense. Before a client goes spending massive capital on drilling holes in the ground or building, huge roof catchments, the simplest step is storing the municipal water we already have.
Yes.
And according to the source, municipalities actually mandate this now.
They do, yeah. The bylaws put a hard mathematical number on what is expected from you. If you have premises that require a continuous supply, you must store not less than 24 hours of demand if you're in an urban area.
And 48 hours for rural areas, which makes sense. I mean, the infrastructure is spread out, so if a main bursts in a rural municipality, the repair turnaround time is naturally going to be longer.
Exactly.
The Drakenstein 2023 bylaw is actually cited in the text as a prime example of this standard requirement. But here is where I see things go off the rails, and I want to push you on the engineering mechanics of this.
Okay, let's hear it.
A lot of clients view a storage tank as a passive bucket. Like you fill it, you park it in the sun, you ignore it.
A passive bucket trap.
Yeah. But a tank is an active part of the plumbing. So what is physically happening to municipal water when it just sits in a plastic tank for 48 hours?
Well, it degrades. And it degrades rapidly. See, when water enters your client's tank from the municipality, it has a residual amount of chlorine in it.
Right, to keep it clean.
Exactly. That chlorine is what keeps it sterile in the pipes. But as that water just sits there in a static tank, that chlorine dissipates into the air.
It just off-gases.
It off-gases, and it also gets consumed reacting with any trace organics in the tank. And once that disinfectant barrier is gone, The temperature inside the tank fluctuates, and biofilm begins to form on the plastic walls.
Oh, gross.
Yeah, bacteria multiply. It becomes a complete breeding ground. This is precisely why the current edition of SANS 241 actually brings static tanks directly into the monitoring regime.
Just to ground us real quick, when we mentioned SANS 241, we were talking about the South African National Standard for Drinking Water Quality, like the absolute legal benchmark.
Correct. SANS 241 doesn't allow you to just test the municipal feed and then ignore what comes out of your tank.
Oh, I see.
You have to prove the water exiting the tank meets the standard. So the engineering best practices are really strict. Tanks must be opaque.
So that blocks the UV light and stops algae from photosynthesizing, right?
Exactly. And vents must be heavily screened to keep out dust, birds, insects, all of that. But most importantly, the plumbing must be designed for active turnover.
Active turnover.
Yeah, you cannot have the tank sitting on a dead-end line. The water coming into the building needs to continuously cycle through that tank during normal operations to keep it fresh.
But let's say the water has to stand. Like a factory closes for a long weekend, or it's the December holidays and nobody's there. The water stagnates.
Right.
The source gives us hard numbers on how to resecure that water before it enters the building. We either need a UV barrier at the building feed, or we have to redose chlorine.
And if you are redosing chlorine, the World Health Organization criterion is the benchmark here. You need to hit 0.5 milligrams per liter of free chlorine.
Okay, 0.5.
And you must guarantee 30 minutes of contact time before that water reaches a tap.
Wait, 30 minutes of contact time. So an installer can't just put an injection pump on the pipe 2 meters before the kitchen tap.
No, absolutely not. That is a classic design failure. Disinfection is a function of concentration multiplied by time.
Okay.
If the chlorine doesn't have the time to physically penetrate the cell walls of the pathogens, well, the water isn't safe no matter how much chemical you dumped in.
And the chemistry of the water itself matters too, right? Because the article explicitly states you have to keep the pH below 8 when chlorinating. Why does pH matter? I mean, chlorine is chlorine, isn't it?
Not quite, no. And this is a really crucial mechanism for engineers to grasp.
Right.
When you add chlorine to water, it actually splits into two different compounds. You get hypochlorous acid and hypochlorite ions.
Okay, acid and ions.
Right. Now, hypochlorous acid is highly lethal to bacteria. It punches right through their cell walls. But hypochlorite ions are terrible at it.
So you want the acid form.
You want the acid form, exactly. And the ratio between those two forms is entirely controlled by the pH of the water.
Oh, wow.
Yeah. If the pH climbs above 8, the reaction heavily favors the weak hypochlorite ions. Your disinfection efficiency essentially drops off a cliff.
Even if you're hitting the dose.
Even if your dosing pump is hitting that 0.5 milligrams per liter target perfectly.
That is fascinating. It's not just about adding the chemical. It is about controlling the environment that the chemical operates in.
Exactly.
Now, before we move off municipal storage, there's one mechanical rule in the text we cannot skip. It's about how you feed the tank. The text states you need a mandatory air gap or an approved backflow preventer on the incoming municipal line.
Yes, and that is a foundational rule of public health engineering. Just think about the physics of a municipal water network for a second. It's under pressure, right? But if a massive main bursts down the street, all that water rushes out of the break, and it creates a massive vacuum in the pipes behind it.
Oh, it's exactly like drinking with a straw.
Yeah.
If the main depressurizes, it sucks the fluid backward.
Exactly. So if your client's tank is hard piped directly into the main, I mean, if their straw is sitting in that stored water, their private, potentially stagnant tank water gets sucked right back into the public drinking water grid.
A massive vacuum.
Yeah, a massive vacuum. And without that air gap breaking the physical connection, you poison the municipal supply.
Wow.
You have to decouple the private system from the public main. It's non-negotiable.
Okay, so that handles the grid. But let's follow the chain of causality here. If the municipal grid goes down for a week, that 48-hour storage tank eventually runs dry.
It does.
Tanks are great, but they still rely on the municipality eventually returning. Let's say our client wrote that food processing plant from earlier, and they absolutely cannot risk relying on the grid. They need total independence.
Enter the borehole.
Enter the borehole. And boreholes are serious business in South Africa.
Right.
The article notes that groundwater already supplies roughly 15% of South Africa's total water use,
Yeah.
drawing from over 1 million boreholes. But the bureaucracy, man. The text talks about a general authorization limit of 10 cubic meters per day.
Mm-hmm.
Like, as long as you pull less than 10 cubic meters a day, you just need to be registered.
Are they really monitoring this that strictly?
They absolutely are, because aquifers are shared national resources.
Hmm.
I mean, the moment you cross that 10 cubic meter threshold, which, let's be honest, any serious commercial operation will do before lunchtime,
Right.
the legal reality shifts completely. You require a formal water use license from the National Department.
Which requires hydrogeological studies, specialist consultants, a lot of waiting.
Correct. Plus, municipal bylaws almost always add their own mandatory metering on top of that.
Oh, really?
Yeah, you have to prove with data exactly what volume you are pulling out of the ground. Right, okay, so let's say the client gets the license, the rig arrives, they drill the hole, and they hit water. Now we face the geological reality, because groundwater is basically a geological mystery box. You have no idea what you are pumping until the lab tells you.
Exactly.
So we need to map out the common South African groundwater threats detailed in this text.
Yeah, the regional geology dictates everything about your treatment train. So the most ubiquitous culprits we see across the country are iron and manganese.
Okay, but those are aesthetic, right? I mean, the SANSAS 241 limits mentioned are 0.3 milligrams per liter for iron and 0.1 milligrams per liter for manganese.
Yeah.
If a client is just using this borehole for, say, a commercial washdown or industrial cooling, why should they care about spending capital to filter out something that just causes a bit of staining?
Because it doesn't just stain, it actively destroys engineering infrastructure.
Oh.
See, when iron and manganese hit the oxygen in the air, they precipitate out of solution and they form these solid metallic sludges.
I see.
And that sludge will foul your pipes, it will destroy your pump impellers, and completely blind any expensive downstream filtration membranes.
So it's an equipment protection issue as much as a water quality issue.
Exactly.
How do we actually remove them then?
Yeah.
The text mentions oxidation, followed by catalytic media filtration. What is the mechanism there?
So you basically speed up nature. You dose an oxidant like chlorine or ozone into the water to force those dissolved metals to turn into solid particles.
Oh, okay.
Then you pass that water through a catalytic media bed. The media is coated with manganese dioxide,
Right.
and that acts as an electron transfer surface. It aggressively pulls those solid metal particles out of the water and traps them in the filter bed.
And then you just backwash it away.
Exactly. You backwash it right down the drain.
Okay, so that handles the metals. What about the unseen health threats? Because the text specifically flags nitrate.
Oh, nitrate is a massive acute health issue, particularly in a geographic band across the Northern Cape, Northwest, and Limpopo provinces.
Oh.
It often comes from agricultural runoff or even concentrated natural geology. And the acute health limit in SANS 241 is 11 milligrams per liter as nitrogen.
And nitrate is dangerous because of how it binds to hemoglobin in the blood, right? It physically stops the blood from carrying oxygen.
Exactly. It causes methemoglobinemia. You really cannot mess around with nitrates. And standard sediment filters won't even touch it.
So what's the treatment?
The required treatment is an ion exchange.
Ion exchange. Okay. So that's swapping molecules. How does that work in a commercial plant?
Think of it like a chemical sponge.
Okay.
You have a tank filled with a specialized synthetic resin, and that resin is loaded with harmless chloride ions.
Right.
As the nitrate-heavy water flows through the resin physically prefers the nitrate. So it grabs the nitrate out of the water and releases a chloride ion in its place.
Swapping a dangerous ion for a harmless one. That makes sense. The text also mentions fluoride having regional spikes, with a strict limit of 1.5 milligrams per liter. But the real financial cliff edge here seems to be salinity.
Oh yes. Total dissolved solids, or TDS.
Let's define TDS for a second for the listeners.
Yeah.
If I take a liter of this borehole water and boil it completely dry, the white crusty powder left behind at the bottom of the pot, the physical mass of all those salts and minerals, that is the TDS.
That is a perfect definition, and the source notes that when your TDS starts approaching the 1,000 milligrams per liter mark,
Right.
SANS 241 actually classifies that water as a desalination candidate. It's essentially brackish at that point.
And standard filtration or even ion exchange can't handle that volume of salt, right?
Not efficiently, no. The only viable treatment for that level of salinity is reverse osmosis.
RO.
Yeah, you have to physically force the water through a semi-permeable membrane under immense high pressure, just leaving the salts behind.
Which is incredibly energy intensive and expensive. Which leads perfectly to what I think is the golden rule for any installer or engineer listening.
Yes.
You have to budget for the treatment train based on the lab analysis, not the sales brochure. Because if you budget for a simple pump, drill the hole, and then the lab comes back with a TDS of 1,200 milligrams per liter.
Then you're in trouble.
Yeah. Suddenly your client needs an RO plant that costs 10 times the original budget.
It happens constantly, unfortunately. The water chemistry dictates the design, period. And there's one final, non-negotiable step here. If that borehole water is intended for potable use, the entire treatment train must finish with a disinfection barrier to secure it microbiologically.
Right, okay. So the grid fails, tanks run dry. Boreholes are a massive headache of scaling salts, nitrates, and expensive RO plants. I can completely see why a client would stand in their factory parking lot, look at their massive warehouse roof, and say, hey, why don't we just catch the rain?
Oh, happens all the time.
Right. It's free, it's soft, let's just use that. But catching rain introduces a totally different kind of threat, doesn't it?
It does. It introduces a biological threat. There is this really pervasive myth out there that rainwater is perfectly pristine because it comes straight from the clouds. But the source totally shatters that idea.
Yes, it points out a really surprising fact. Harvested roof water might look and feel clean, but South African tank water studies routinely find E. coli and opportunistic pathogens in those samples.
It's true.
And when you think about it mechanically, it makes total sense. That rain is falling through atmospheric pollution and then washing over a massive roof covered in bird droppings, dust, decaying leaves, straight into a dark, warm tank.
Yeah, it is basically a bacterial soup, which means as an engineer designing a rainwater system, you have to force a strict practical split. You have to ask, is this water for non-potable use or potable use?
Okay, let's start with non-potable. Say the client just wants to use the rain to flush factory toilets or irrigate the landscaping.
Well, the engineering there is relatively straightforward. You need coarse filtration to keep the leaves out, obviously, and a first flush diverter.
Explain the first flush diverter for us.
It's a simple mechanical trap, really. When it first starts raining, the water washes all the accumulated dirt and bird droppings off the roof.
Right, that initial wash.
Exactly. The diverter captures that first, highly contaminated volume of water and routes it straight to the stormwater drain.
Oh, I see.
Only after that dirty water is flushed away does the diverter allow the cleaner, subsequent rain to actually enter the storage tank.
That's simple, but really effective.
Yeah.
But even for flushing toilets, the municipal guidelines are incredibly strict about how you plumb that rainwater into a commercial building.
Because of the cross-contamination risk.
Right.
The non-potable rainwater lines must be completely separated from the building's potable municipal lines.
That makes sense.
If there are any interconnections, say like a backup feed to keep the toilets flushing if the rainwater tank runs dry,
Yeah.
you must have industrial-grade, reduced pressure backflow preventers installed, and every single non-potable tap requires mandatory do not drink signage.
Because you can easily imagine, like, a factory worker filling up a water bottle from an irrigation tap on a hot day.
Exactly. You have to design for human behavior.
But what if the client does want to drink it? What if they want to use that harvested rainwater for food preparation in their staff canteen? What does it physically take to make roof water legally drinkable?
Then it stops being a simple storage tank, and it basically scales into a full water treatment plant.
Really?
Yeah. The mandatory train laid out in the text starts with that first flush diversion we talked about. Then you run the water through fine sediment filtration to physically catch the microscopic particulates,
Okay.
and then it goes through carbon filtration.
And carbon isn't for particulates, right? Carbon handles the dissolved organics.
Exactly. Activated carbon operates through adsorption with a D.
Adsorption, right?
It has millions of microscopic pores that trap the dissolved organic compounds that cause bad tastes, odors, and chemical contamination.
Yep.
But carbon doesn't kill bacteria. So the final step is a mandatory active disinfection barrier.
So back to UV or chlorine.
Exactly. That usually means a validated ultraviolet light system to scramble the DNA of the pathogens or automated chlorination.
Man, it is a highly engineered sequence.
It has to be, because the unifying goal of this entire article, the absolute baseline the law requires, is that whether your water comes from the rain, a borehole, or a municipal tank, the ultimate destination at the point of use is always SANS 241.
Right.
You do not get a pass on the microbiological health limits just because the water originally fell from the sky.
So let's distill this for a second. What are the rules of thumb for the engineer standing on site today?
Let's hear them.
First, your primary defense is storage. Store a day or two of demand as your baseline, so 24 hours urban, 48 rural, and keep it actively circulating.
Yeah.
Second, only drill a borehole if the client's business case actually justifies the bureaucracy and the complex chemistry.
Absolutely.
Third, always design your treatment train based on a comprehensive lab test. never on assumptions.
Never.
And finally, end every single system with a robust disinfection barrier and hold the SANS 241 test results in your hand to prove it works.
That is an excellent summary, but I want to bring up one final detail from the article before we go.
Okay, what is it?
It's mentioned almost in passing, but for an engineer, it completely changes how you look at a project. The text notes that boreholes, quote, drift with seasons and abstraction.
Drift, meaning the physical chemistry of the groundwater isn't permanent.
It isn't permanent at all, and I want to leave our engineering audience with this to chew on.
Yeah.
The water chemistry you design a treatment plant for today, based on today's lab results, is just a snapshot in time.
Wow, okay.
If a massive new agricultural development opens next door and starts pumping heavily, or if the local aquifer drops over the next 5 years due to a regional drought, the dissolved solids and the minerals in your client's borehole will concentrate.
So the TDS shoots up.
Exactly. The chemistry will change. So as an engineer, are you designing a rigid static installation that will fail when the water changes? Or are you building a dynamic modular treatment system that can adapt to the shifting geology beneath your client's feet?
That is the ultimate question, isn't it? Designing for tomorrow's water, not just today's snapshot. Well, that is all the time we have for this deep dive. Go pull up the article on the DWT website, check your assumptions at the door, and keep designing smart.